Hi, I wanted to share with you two IB problems specifically this morning. And so the first one is coming from paper number one, right? Paper number one. This is the no calculator part of the test. And this is from the 2018 test. So I want to show you a question on this and talk about the way that it's worded. Then we're going to also look at a question from last year's test that was on paper number two. So here's the first question. It was question number 11. You can go to Google Drive and open up this test if you'd like to. Question number 11. This is a pre-calc topic, but the way that they word some of the things caused a lot of students trouble. And so that's the purpose of this video, is really just to talk about the wording and to refresh your memory a little bit. We'll work through some of these. So what they've done is they've given you this equation right here. Now notice, if you look at this carefully, what this represents is not a function, right? Because there's no variables here. This is a number. So W is an imaginary number. W is a complex number, more correctly. And then they're asking you to do a couple different things with W. But the main thing, and like I said, we'll work through this in a second, but the main thing I want to make sure we focus on is this vocabulary right here. What is modulus argument form? What does that mean? And then this vocabulary right here, sketch on an Argand diagram. So what is an Argand diagram? What is that? So we're going to focus on those two topics here in just a second. Let me grab some paper and we'll get started.
In this first video, they've given you a number that they've called W. And in part A, they ask you to do two things. The first thing they do is they ask you to express W squared and W cubed in what they call modulus argument form. That's the first thing they ask you to do. Okay. Now, take a look at the formula sheet for me. With me.
Okay, so if you look at the formula sheet, and again, remember, you will have a copy of this while you're taking your test. In the first topic, topic number one, algebra, so this is your first page of the formula sheet. In section 1.5 and 1.7, these are your formulas that you're going to need as far as complex numbers go. And so the first one right here in section 1.5 gives you your different forms for complex numbers. Now, I'm not sure what you called these when you did these with Mr. Smith, but the first one that we've got right here, this is what we call the rectangular form, a plus bi. That's the one that most of us are more comfortable with or more familiar with. Then next to it, we have r times the quantity cosine theta I sine theta. That is your modulus argument form. Okay, so when they ask you to write your answer in modulus argument form, that's what they're looking for, is that right there. The next thing next to that is Euler's form, and then the last thing is cis theta form. And so the cis theta form is really just a shorthand that we use when we're working. I'm sure you probably used that last year with Mr. Smith. It's okay to write that on a test. Just make sure if they ask for your answer in modulus argument form that you make sure your final answer is written that way. And then we have Euler's form. So getting back to our problem.
In the problem, you can see that the equation or the expression they gave us to start with, this is modulus argument form. That's what we're looking for, okay? So that's the idea that we're trying to find here. So if I'm going to do W squared and W cubed and write it in that form, the easiest way to do that is to use De Moivre's theorem. So let's go back to the formula
so
sheet
in section 1.5 of our formula sheet, that was where we found the different forms for the complex numbers. But right underneath that, in section 1.7, that's where we find De Moivre's theorem. So what you can see this theorem does is it shows us different ways that we can find powers of complex numbers. These are all equivalent. So if it's in modulus argument form and we raise it to a particular power, the most useful and the way that we generally use this theorem is to write it still in modulus argument form, but notice what's happened. The exponent distributed into the to the r, but through some trig identities that you would have proven last year with Mr. Smith, instead of having cosine raised to the n power or sine raised to the n power, what have you, what that does is it ends up becoming a coefficient on theta. And so I get r to the n times the quantity cosine of n theta plus I times the sine of n theta. And so this is what we're going to want to use as we try to evaluate w squared and w cubed.
So on this particular problem, if I take 2 cosine pi cubed plus I sine, not pi cubed, pi over 3. If I take this thing and I square it, then according to De Moivre's theorem, we'll end up with 2 squared times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. Now, as far as simplifying that, there's only one thing I need to do. What does 2 squared equal? And so now this is an expression that's in modulus argument form. So that's all we have to do in part 1 for w squared. W cubed would be the exact same idea. Now we would just, instead of a 2 in these 3 spots, there would be a 3 in those 3 spots. So if that's w squared, w cubed is going to be a 2 cubed, which is 8, times the cosine of pi over 3 times 3, which is pi, and then the sine of pi. And that would be our answer there. So that's all you're needing to do in part 1. In part 2, they ask you to take those 2 results, but also w to the 0 power and w to the 1st power, and they ask you to graph all of those on something called an Argand diagram. Okay, so before we get to this, let's just make sure we're comfortable with these 2 things, right? Anything to the 1st power is just itself, and that would still hold true if we used De Moivre's theorem, because 2 to the 1st power would be 2, and then 1 times pi over 3 would still be pi over 3. We'd get the same thing. So this is that. We're good there. So what about w to the 0 power? Well, in real numbers, we always say that anything that's a non-zero real number raised to the 0 power always equals 1. Is that still true with imaginaries? Well, De Moivre's theorem tells us, right? So if we apply De Moivre's theorem to this, we'll end up with 2 raised to the 0 power. Well, that's 1. And then pi over 3 to the 0 power is going to be, or times 0, is going to be 0. So the cosine of 0, that's 1. The sine of 0, that's 0. So we end up with 1 times the quantity 1 plus 0. So we get 1. So this is equal to 1. This is equal to 2 times the cosine of pi over 3 plus I times the sine of pi over 3. And then these 2 things we've got. Okay, so we've got what those, all 3 of those things are. Now, what an Argand diagram is, you would have worked with these last year in Mr. Smith's class. We just typically don't use that term, at least not very commonly. But an Argand diagram is a method for graphing complex numbers. And the way this method works is that the horizontal axis becomes your real axis, and your vertical axis is your imaginary axis. And you graph these complex numbers exactly the same way you would graph xy coordinates, which means to do that, we have to convert all of these into their rectangular form. So in rectangular form, w to the 0 power would be 1 plus 0i. So this is my horizontal, and this is my vertical component. So w to the 0 power would be over 1 on the real axis, up 0 on the imaginary axis. That is w to the 0 power right there. W to the 1st power, I'm going to have to convert these, right? So pi over 3. Make sure we're comfortable with our unit circle. I'll give you a second to think about it. Cosine of pi over 3 is going to be 1/2. Sine of pi over 3 is going to be root 3 over 2. If I multiply both of those by 2, I'm going to get 1 plus the root 3i. And so that tells me my horizontal component is over 1, and my vertical or my imaginary component is up root 3. So square root of 3 is going to be a little bit more than 1, so let's just say we're somewhere around there, give or take. So there's w to the 1st power. Now, w squared, I'm going to get for cosine, I'm going to get a negative 1/2, And for sine, I'm going to get a positive root 3 over 2. Multiply those by 4, and I get a negative 2 for my real component. And I get a positive 2 square roots of 3 for my imaginary component. So we're somewhere around there. This is not it. This is it. So you get the idea of how this is working, okay? So the basic idea, actually this is going to be a little bit less than 3 now, a little more than 3. But you get the basic idea. That would be the way that we handle part A. Okay, now if we want to go back and look at some of these other things, it says in part B that if we were to graph all 4 of these things, we would end up with a quadrilateral. If I graph this, cosine of pi is going to equal -1, sine of pi is 0, times 8 gives me a -8. So 1, 2, 3, 4, 5, 6, 7, 8. So there's W3. So I've got this quadrilateral. So the next thing they ask me to do is to find or show that the area of that quadrilateral is going to be 21 times the square root of 3 over 2. Okay, now for this, I'm not sure that I need to go into a lot of detail for this. You can use your normal geometry methods and techniques. I can probably look at a triangle right there, maybe look at a triangle right there, maybe do a rectangle right there. I guess there's a variety of different ways that I might be able to try and find that area. Don't forget that you've got all your different area formulas. You don't have to just simply use 1/2 base times height, right? We can do sines and cosines and things like that. Those formulas are also on your formula sheet. Okay, and then the last thing that you needed to do was to look at a way to generalize the equation of the area of a polygon. So I think what I'd like to do is hold off on that. If you want to take a look at that problem and try that on your own, you can. That might be a good thing to do with your extra time. But the main purpose of this video was I wanted to make sure that we understood this and that we understood this. And I think that we've done that now. If you want to try part C, and then, or even if you want to go back and do part B, finding this area, if you've got questions about that, just let me know.
All right, so that was the first question I wanted to show you. Now we're going to take a look at a question that came from the calculator half of the test. So you can see this is paper 2. Paper 2 is the calculator half of the test. And this was the 2019 test. So this is the test that they took just last year. And the question that I want to look at, this one is actually a calculus topic. Question number 6. Is again an imaginary number. I'm sorry, this is not the question I was thinking it was. However, we are going to take a look at this question too. There's a third question that I had in mind, so I'll add one more to the end of this video to take a look at the other question. But here we have again an imaginary problem dealing with Argand diagrams. Now we know what that is, but we have this notation right here that we need to talk about or deal with. And so I want to talk about what does that notation mean? Similarly, this notation right here, what does that notation mean? And then again, just because it maybe is a good review of complex numbers, we'll work through these problems maybe a little quicker than last time because we've worked through one of these already.
Okay, so in this second video, again, we see in part A that they're asking us to do an Argand diagram. And so I feel like we've just sort of reviewed that in the previous problem. This time it says show the points represented. So it says that Z is equal to A plus BI. And then it says that there's a second number, Z minus 2A. So if Z is A plus BI, then Z minus 2A must be a plus bi minus 2a. And so that's going to be the opposite of a plus bi. Now, information that's given in the initial problem is that a and b are both this. Okay, and since our purpose in this video is to make sure that we're comfortable with reading notation on the IB exam, let's make sure we're comfortable with this. Hopefully we recognize this and this. These are symbols we've used frequently in our class. This is the symbol for is an element of. That means a and b belong to the set. And this is symbol for the set of real numbers. So a and b belong to the set of real numbers. In other words, a and b are real numbers. But this notation, that means that strictly it's the part of the real number set where things are positive. So in other words, a and b are positive real numbers. But what we find over here then is because I have the opposite of a, and a is given to be a positive real number, in this expression, our real part is going to be a negative value. Okay, so on this problem, they actually gave us the axes we need for the Argand diagram. So if you did not know that this was an Argand diagram, you would be saved because they give you that information. And they say, now let's show the points represented by z and z minus 2a. So for this, we're just going to find arbitrary values of a and b. So let's just say that this is over a and this is up b. Okay, we don't know exactly what the values of a and b are. We just know they're positive. So this satisfies that. That would make this point z. And if these two things are a and b, then that would make this the point that's associated with z minus 2a. Okay, so that would be our answer from part A. Now, part B, and this is really more the focus of this particular video, it asks us in part 1 of part B to figure out what this is. Whoops, this was minus 2a. Okay, figure out what that is. So this notation is notation that you are also expected to know. Let's take a look real quick at the list, not the formula sheet that you're provided, but the list of notation that you're expected to.
All right, so this is the first page of the notation list. So remember, in the IB materials that you received last year from Mr. Smith, and then there's copies of them also on the Moodle page, you have the formula booklet, which I think at this point you're all familiar with. But you also have two other documents. One is the notation list, and this shows all the different symbols that you're expected to recognize on the test. And then the last thing that's there is the list of command terms. Those are the terms that will show up in directions. And so to make sure that you're doing exactly what the question is asking you to do, you need to know those command terms. So those are documents to make sure you review. In the notation list here, I've highlighted the section of the list that deals with complex numbers. Although notice for a second real quick, there's our chalkboard bold R with the plus sign, right? So there's telling us that it's the set of positive real numbers. So that's just what we just talked about a second ago. But here are all our complex number things. And what we're going to talk about right now are these four, bar z, arg z, re z, im z, these four right here. So bar z, that is the modulus of z. Remember, modulus, it's a very similar to absolute values, which is why the symbol looks very similar to absolute value. Modulus is finding the distance that the complex number is away from 0. And of course, in an Argand diagram, 0 is like the origin. So it's kind of like finding how far a point is away from the origin. So basically, the way we find a modulus is like using the distance formula. Argument is when we look at something that's in modulus argument form, the argument is the theta values. And so that's what we're going to be working with in this problem, is we're going to be trying to find the value of theta. REZ means find the real part. So we talked about if it's written in rectangular form, then a plus bi, the a is the real part. So that's what this is. And then IM, that's the imaginary part. So if it's in rectangular form, the B is the imaginary part. So these are the different symbols. You are expected to know these. If you have not looked at this list recently, then I suggest you definitely start thumbing through that list. There's a couple different symbols here that are important for you to know. The main thing that sometimes throws students for the loops is a lot of the symbols they use in geometry are different than the standard symbols we use here in America. So definitely make sure you pull out this document and look through it.
Okay, let's get back to our problem. So if this is trying to find the argument of this, that reminds us then of modulus argument form. And in modulus argument form, the reason it's called modulus argument form is because r is the modulus. That is going to be the distance that z is away from the origin, away from 0. And theta, that is the argument. And so what we're trying to do is we're trying to find that. That's what we're trying to find. So if you remember the way this works, let's go back to our Argand diagram, because it's the Argand diagram that enables us to do this. What I have right here is I've got this point, and this point can be considered as being the end of a line segment. And if I do that, then the length of this line segment, that's my modulus. But that's not what we're interested in right now. What we're interested in right now is the argument. And the argument will be the angle that that line segment forms with the positive x-axis. So this is what we're trying to find, is that thing right there. Now, obviously, the nature of this problem, because we don't know actual values for a and b, our answer is going to have to be expressed in terms of a and b. So what we're going to end up with, in this case, is our a value and our b value functionally, whoops, b is going to be this, a is going to be this, are forming the two legs of a triangle, which means that this angle that we're going to have here is going to be a tangent value, or an arctangent value. So theta is going to be provided by the arctangent of negative a, I'm sorry, it's opposite over adjacent, right? So it's positive b over negative a. Opposite over adjacent. Okay, but there's a small problem, because we know that arctangents give answers that are either in the first or the fourth quadrant, and ours is clearly in the second quadrant. So the last thing that we're going to need to do then is say that this is going to need to get moved from the answer that's down here around to there, which means we're going to need to add on to this pi units. And this would be my expression for the argument of z minus 2a. I know I haven't finished the problem all the way through, but I am going to stop there. Like I said, I would encourage you to try to finish this problem the rest of the way through. If you get stuck, if you're not sure what to do, if you get hung up on something, shoot me an email, let me know. I'll be glad to help. But for the purposes of our video, I wanted to review this notation, and I think at this point we have achieved that. So good luck. Let me know if you've got questions or concerns, and we'll talk later.